Hello and welcome to this FMSP online revision recording for the OCR specification module M1 Mechanics. The topic is Newton's laws of motion, and under that heading in the specification we see three sections. The first is about using Newton's laws of motion for bodies of constant mass moving under the action of constant forces. So for example, with constant masses, we're not considering for a car travelling along that its mass diminishes as petrol is used up. We'd consider the mass to be constant. Number two, modelling in suitable circumstances the motion of a body as motion with constant acceleration. And consider limitations of this model. Well, typically the simplifications we're making are to reduce the object we're talking about to a particle, and one consequence is that we're ignoring air resistance. So that's an example of a limitation to the model. If we'd included air resistance, perhaps our calculation would be slightly truer to life. Then the third point is about connected particles, the motion of two particles connected by a light and extensible string. And the strings are always light and inextensible. We can ignore the mass of the string, there's no elasticity to be concerned about, and if they pass over a peg or a pulley, then those are always smooth and there's no friction there to be concerned about either. So let's remind ourselves about Newton's laws. Newton's first law. A body will continue to remain at rest or move at constant speed in a straight line unless an external force makes it act otherwise. Remember, forces make a body accelerate or decelerate. Secondly, Newton's second law. A resultant force acting on a body produces an acceleration which is proportional to the resultant force. Well, in SI units, that's F equals ma, which is the form in which we should use Newton's second law every time. And then Newton's third law. For every action, there's an equal and opposite reaction. And when we're looking at connected particles, that particularly means that we're putting in two tensions, or two thrusts, in opposite directions. So let's have a reminder about connected particles and Pulley questions. First of all, it's very important to do a big clear diagram which shows all the forces. And Newton's third law tells us that if there's one tension acting along a string in one direction, there must be a second tension acting the other way. Always add tensions in pairs. And then label the acceleration by both the particles. Occasionally there's a third particle, so I say all there. And write separate equations of motion for each particle, and typically you're going to write two equations and add them to eliminate tension. So what is it that connected particles share? Well, typically you've got the same tension at either end of the string or the tow bar acting on both particles, but in opposite directions. If they're connected by an inextensible string, once they move, they're going to share the same acceleration. And they're going to move the same distance. And if they're speeding up from rest, they'll reach the same velocity. Let's see some questions then. And here's the first one. If I go through the question very quickly, just remember you can always pause the recording and read the question at your leisure. So we have a block lying on a smooth slope inclined at 30 degrees, attached over the end of the slope over a smooth pulley to another particle hanging vertically. This is particle P. We know the mass of the two particles, and what we're going to find out is what's the acceleration of B and the tension in the string, and then the magnitude of the force exerted by the string on the pulley. Then there's a little bit of suvat. The initial speed of P is a certain amount because it's projected vertically downwards when the motion starts. It travels 1.5 meters downwards and hits the ground, and what happens to B, which is continuing to move up the slope? What distance does it travel before coming to rest? Okay, let's answer all of those and start with a nice clear diagram with everything on it. And always make the slope of an inclined plane sufficiently clear that you can label components of forces on without too much difficulty. So this is inclined at 30 degrees, reasonably generous 30 degrees on my sketch. So we have the block on the plane, and this is B, whose mass is 0.85 kilograms. That's attached over a pulley by a continuous string to another mass hanging downwards, and this one is P. The mass of this one is 0.55 kilograms. Clearly there's going to be a tension acting upwards on B and supporting P. Let's put in the weight of P, and of course that's just the mass in kilograms times G, newtons. But the weight of B I need to write vertically. I'm going to label it to the left there because I'm going to put some components to the right. 0.85 G newtons, and I think I'm going to end up splitting that into components perpendicular to and parallel to the plane. We also have a reaction force because the block B is in contact with the plane. So there's my force R. I think if we let go it's going to accelerate to the right, and this is significant. Label the acceleration by both particles because both particles will share the same acceleration and both of them are experiencing the same tension. Now let's put on those components on B. If this angle is 30, then the angle in here is also 30 degrees. And so for the component opposite the angle, it's 0.85 G sine 30. And for the one next to the angle, 0.85 G cos 30. And now we're ready to start considering the components. First of all, let's look at B. So for mass B, let's consider what's happening parallel to the plane. Well, I've got a force up the plane of magnitude T. Don't know that yet, I'll find that out in a minute, minus the component acting down the plane, the component of the weight, 0.85 G sine 30. And all of that is equal to the mass, 0.85, times the acceleration, also at the moment unknown. Well, there's equation 1. Now let's consider what's happening for P. And we're resolving vertically here for particle P. Well, take the direction of the acceleration as the positive direction. So in the direction in which A is positive, we have 0.55 G downwards minus T in the opposite direction. And that'll be equal to the mass, 0.55, times the acceleration, and there's equation 2. You can see from these two equations what we normally see, which is that T is positive in one and negative in the other. So our best option is to add equation 1 and equation 2. Adding those together, I'm going to have, taking the bottom one first, 0.55 G minus t, then the first one above, plus t minus 0.85 g sine 30. And that's equal to, adding the right hand sides, 1.4 in total, A. Well, that means I can find A simply by taking this side and dividing by 1.4. Of course, G is 9.8, so I know that. 0.85 G sine 30. Sine 30 is 0.5, so this might come up with quite a tidy answer. Divided by 1.4. And in fact, we find out from this that A is exactly 0.875 meters per second squared. That's a tidy, exact value for later use. And let's substitute that into equation 1 to find the tension. Now, equation 1, if I were to add a term to both sides, I could have T equals, well, let's add 0.85 g sine 30 to both sides, and I'll get T equals 0.85a plus 0.85 g sine 30. Well, we know A, so this is 0.85 times the acceleration of 0.875 plus 0.85 g, so that's 9.8, times sine of 30. And from that, I get a tension which I make 4.90875, so 4.91 newtons, to 3 significant figures. Okay, there's a further part to this question then, which says, find the magnitude of the force exerted by the string on the pulley. Okay, I'm going to add that little bit and do the calculation over to the side here. So as far as the pulley is concerned, what's acting? Well, remember Newton's third law, add the tensions in pairs. From the point of view of the pulley, there's a tension acting downwards here, and there's the same tension acting along the string in that direction. I know the magnitude of the tension, it's 4.91. But how much of it is acting on the pulley? Well, if you imagine a line of symmetry through this pulley, and I do know the angle at the top there, if this is 90 degrees, then the total angle there is 60, which makes both parts of this angle 30 degrees. Then if I were to resolve these two tensions, I could have a component. If I take, for example, this top tension here, I could resolve it into a component in this direction and a component perpendicular to the string. I'm going to draw the perpendicular components across here, because in fact that component is going to equal this component. So resolving into perpendicular components, a bit hard to see on my diagram here, but I'm going to have T sine 30 up here and also there. Those two are equal and opposite. And the other component in there, which is T cos 30, there's two of those. Okay, it's all a bit unclear over there, so let's write it out nice and clearly here. The force on the pulley is equal to 2t cos 30 degrees. Well, that's equal to 2 times 4.91 cos 30 degrees. And in total that is 8.50 newtons 3 SF. And let me just say that, as with all calculations, I've used the exact value stored in the calculator from the tension previously, so that I don't lose any accuracy finding the force for this. Okay, let's move on from there and keep the piece of information which matters most, that the acceleration is 0.875. Let's find out what happens when everything is released from rest. Now we're told that particle P, which was the hanging particle, is projected downwards with an initial speed of 1.3 meters per second. Well, obviously, if they're connected, the same is true of B. So both of them have the same initial speed. The question says calculate the distance B moves up the slope before coming to rest, given that P hits the ground after 1.5 meters. So the first thing I'd like to know is, how fast is B going when P hits the ground after 1.5 meters? Well, what do I know about B? I know that its initial speed, same as P, is 1.3 meters per second. Its acceleration, which we found in the previous part of the question, is 0.875 meters per second squared. And it will have gone 1.5 meters. We'd like to know, how fast is it going now? Because that'll be the speed which we need for the second part of the calculation. Okay, well, I've got V, U, A and S, so my best choice of formula will be V squared equals U squared plus 2AS, which gives me V, which I'm trying to find, squared equals 1.3 squared plus 2 lots of A, 0.875, times S, which is 1.5. Well, the easiest thing to do is pop all of that in the calculator, and it comes out exactly that V squared equals 4.315. Now I want to know the speed, so I'll write it down, and it's 2.077 etc. meters per second. But actually, although I might in the question write that down as perhaps 2.08 meters per second to 3 significant figures, the exact value is the square root of 4.315, and that's what I'm going to use later on. So actually this line is the one I'm going to come back to. Okay, what happens once that string breaks? Well, at that point the only acceleration will be the component of the weight down the plane. So let's ask myself, what is the new acceleration of B? And I'm going to use F equals ma to establish that. Bear in mind B is moving up the plane. I'm going to treat up still as my positive direction. There's a weight component down the plane. It's 0.85 g sine 30. And that's equal to the mass, which is 0.85, times the acceleration. Well, clearly those two 0.85s will cancel out, and that leaves me with the acceleration equals minus g, which is 9.8, times sine 30, which is 0.5. That gives me a nice answer that A is exactly minus 4.9. So for the next part of the calculation, I'm going to use an acceleration of minus 4.9 meters per second squared. So now back to Suvat to finish off. And what's happened for B? Well, after travelling 1.5 meters, let's just make a note of that. Because I want the total distance it travels. The first thing it's done is travel 1.5 meters. What's happened at that point? I have a new speed. It's the square root of 4.315. That means I haven't lost any accuracy. What's the acceleration? Well, it's just become minus 4.9. meters per second squared. I'd like to know when does B come to rest. So V is 0, and I particularly want to know how far it's gone, because I want the total distance it travels before coming to rest. This is all assuming it doesn't hit the pulley, and we are told that in the question. Well, once again, I've got UA, V and S, so I want V squared equals U squared plus 2AS. V squared is 0 squared. U squared, well, given it was a square root to start with, U squared is 4.315. Plus 2 lots of, and the acceleration is minus 4.9, times S, which I'm trying to find. So that gives me 0 equals 4.315 minus 9.8 times S. Let's add 9.8S to both sides. 9.8S equals 4.315, and therefore S is 4.315 divided by 9.8. That gives me an answer of 0.440 meters to 3 significant figures, and therefore my total distance before coming to rest is this plus the 1.5 meters already travelled. 1.5 plus 0.440, and that gives me a total of 1.94 meters to 3 significant figures. And that concludes the first question. Here's the second question I want to look at. This is a connected particles question. We have a block of mass 0.8 kilograms, and it's being pulled to the left by a force. We're told there's an acceleration of 0.2 meters per second squared. And towing behind it, there is an object P, which is in contact with the plane, and whereas B makes smooth contact with the plane, there's friction between P and the surface, so there's a value of mu to be found here. Of course, we need to put in tensions in this light inextensible string, one here and one here. Now in a moment I'm going to redraw the diagram so it's easier to put all the components on, but those two tensions are equal and opposite, and both are inclined at that angle of 10 degrees in the string. Okay, I'm going to redraw the diagram, and what we're looking for is, first of all, what's the magnitude of the tension. Once I've found the value of the tension, I'm going to find the coefficient of friction between P and the surface. Okay, let's draw the diagram first then. I want to make sure I've got everything, including those components, clearly drawn on. So this is the block that's in smooth contact, 0.8 kilograms. So there's no friction to be concerned about here. There is the force pulling it forwards, which is 2 newtons. Of course, because it's got a mass, it has a weight, and that is 0.8 g newtons. And because it's resting on the surface, there's a reaction force. I'll call that one R. And we're told the system is accelerating at 0.2 meters per second squared. Now then, it's dragging behind it this other particle. Just want to exaggerate the angle here. And we have an angle of 10 degrees with the horizontal. We have a tension here equal and opposite to the tension here. So what are my horizontal components? Well, here I have a horizontal component, it's next to the angle, so it's t cos 10 degrees. And there's a vertical component, which is t sine 10 degrees. We have the same components on the other particle, t cos 10 here, and the vertical component, t sine 10 degrees upwards. Then what else is going on over here? Particle P has a mass of 0.3 kilograms, so it has a weight of 0.3 g newtons. It's in rough contact with the plane, and there's a value of mu here to be found, but there's friction. And then also upwards there's the normal reaction force. I'm going to call this one N for normal because I've already used R in this question. And of course, don't forget, because they're connected particles, they share the same tension and they share the same acceleration. So the acceleration for this one is also 0.2 ms to the minus 2. Okay, just one more thing I'm going to put on the diagram as a reminder to myself, which is that particle B is in smooth contact with the plane. Okay, let's look at what's going on horizontally for B. Taking to the left as my positive direction because the acceleration is to the left, I'm going to use F equals ma. Don't forget, F doesn't mean a single force, it means the resultant force. So the resultant towards the left is the 2 to the left minus t cos 10 to the right. And that's equal to the mass, 0.8, times the acceleration, which is 0.2. Which means we know the right hand side is 0.16. On the left we've still got 2 minus t cos 10. Well, I'm going to subtract 0.16 from both sides, so on the left I'll have 2 take 0.16, which is 1.84. And I'm going to add t cos 10 to both sides. Well, that means I can divide by cos 10 and get that t equals 1.84 divided by cos of 10. And that gives me a value for t of 1.86838496. Well, I can't write all of that down, but I'll write 1.87 newtons to 3 significant figures, and I'll store the exact value. Okay then, that's that part done. And what we're trying to find for the second part of the question, we found the tension in the string. For part 2 we want to find the coefficient of friction between P and the surface. So part 1 is done, let's do part 2. Let's see what's happening for P. For P then, let's first of all resolve vertically. And vertically it's not hopping up and down on the surface, so these forces must be equal. Ups equal downs. Up I've got N, but there's another force acting on P upwards. In my rather small diagram here it is. It's the component T sine 10. And that's equal to the only force downwards, 0.3 g. Well, I can rearrange that, and in fact I know what t is, so I'll rearrange and substitute in for t at the same time. I'm going to subtract t sine 10 from both sides. Instead of t, I'm going to write 1.87. So it's 1.87 sine 10. So everything on the right hand side can be calculated, and it gives me a value for n of 2.615, etc. Well, it's 2.62 newtons to 3 significant figures. Again, don't be confused by the use of n for the normal contact force and n for newtons. Now, again, store the exact value of that so you can use it in the next part of the calculation. Well, we've dealt vertically, now let's deal horizontally with P. What's going on horizontally? Bearing in mind it's accelerating to the left, let's take the left as the positive direction. Towards the left we have the component of the tension that's pulling it along, T cos 10, minus the friction. And that's equal to the mass of 0.3 times the acceleration 0.2. So that right hand side is exactly 0.6. I'm sorry, 0.06. And on the left, I know t, I know cos of 10, but actually, look over to the left here, t cos 10 is exactly 1.84. And that's minus the friction. Well, if I add friction to both sides, I'll have FR over here, and if I subtract 0.06 from both sides, it'll end up over here. Which means I can calculate the value for FR, 1.84 minus 0.06 is 1.78. Now, because it's moving, friction is taking its maximal value, so friction is mu r. If I divide both sides through by r, that means mu is friction divided by r, and that's the result I'm going to use now to find the value of mu. So given what I know, mu equals the friction, which is 1.78, divided by the reaction force, that's the normal force I've called N, 2.62. Of course, I've used the stored value in my calculator for maximum accuracy here, and that gives me 0.681 to 3 significant figures. And just to say, coefficient of friction doesn't have units. Good. Let's proceed to the last question, which is a pulley question. And I've selected this one because on the page it looks rather unpleasant. It's unusual that we see a pulley with one particle resting on an inclined plane, but this question is certainly not as bad as it looks, because P is in contact with the plane when everything is resting in limiting equilibrium, and as you see, P has a mass of 0.4 and Q of 0.3, so P is the heavier particle at this point, and if it's resting in limiting equilibrium, that's because friction is acting up the plane to stop P sliding down. So we're going to use something about the friction associated with P to establish the first part of the question, and then for the second part of the question, the masses are changed, an extra 0.2 is attached to Q, which then means Q becomes the heavier of the two particles, and at that point you can ignore the inclined plane because Q will move downwards and P will move upwards, and then we can find the tension and the acceleration in the normal way. So let's do that in 2 stages. First of all, let's have a nice clear diagram which shows the components on the plane for the friction that's involved. So I'm going to make that pulley just a bit bigger so everything doesn't all collide on my diagram. There's my inclined plane and my particle sitting here on the plane. So the other one is hanging. I don't really want it to interfere with the other part of the diagram. And this is my other particle, and they are P and Q. Okay, let's put some weights in. The mass of P is 0.4 kilograms. So its weight is 0.4 g newtons. And for Q, its mass is 0.3 kilograms. So its weight is 0.3 g newtons. And because they're connected particles, they share the same tension. And they share the same acceleration, but in this particular case the acceleration is 0 because we're told that the system is in limiting equilibrium. There's a little shorthand for equilibrium. Okay, well, as far as the right-hand side of the system is concerned, that's fairly easy. I can see, looking at Q, that the tension upwards has to equal 0.3 g newtons downwards if it's in limiting equilibrium and at rest. And of course that's the same tension that's acting on P, so I do know that the value of T is 0.3 g. That's a known quantity. So let's see what else is acting. We have friction up the plane here. And we have an angle of 60 degrees, so it's quite steep. And let's resolve this weight force into components perpendicular to the plane and parallel to the plane. Well, if this angle is 60, then the angle in here is also 60. And that gives me 0.4 g sine 60 for the component opposite the angle, and 0.4 g cos 60 for the component next to the angle. Of course, because it's resting on the plane, there's also a reaction force perpendicular to the plane. More about that in a moment when we resolve. And we also need to consider components of this tension force. There's a component parallel to the plane and one perpendicular to the plane, so I need to know this angle in here. And by a little bit of chasing the angles, you ought to be able to see that if that angle is 60 and this one is therefore 30, we have a vertical line here and a vertical tension, and the line parallel is at 30 degrees, so the angle here must be 30. So I have a component of t sine 30 opposite the angle, and one of t cos 30, which I think I'm going to have to label down here, t cos 30, next to the angle. Okay, amongst all that, we now have everything, I think. Let's carry on then. So, for particle P, what do we know? Let's consider the forces perpendicular to the plane first, and that's because it'll enable us to find R, and I need R to deal with the friction. So first of all, perpendicular to the plane, what's going on? Well, I've got R upwards out of the plane and t sine 30. R plus t sine 30. And that's equal to the component in the opposite direction, 0.4 g cos 60. Now, notice cos 60 is a half, So that's going to be something a little bit easier to work out. In fact, this term over here is going to be a half of 0.4 g, so that's 0.2 g. And I'm going to subtract t sine 30 from both sides. But I do know t. T, we found, is 0.3 g. So all of that can be calculated, and sine 30 is also a half, so rather conveniently we get an exact value for the reaction here of 0.49 newtons, exactly. Now let's consider parallel to the plane. So this is considering the friction, and we're trying to find mu. We know r. If we can find a value for the friction, then we can divide to find the coefficient of friction like we've done previously. Okay, what's happening parallel to the plane? Well, parallel to the plane we have the friction up the plane. We've also got a component of tension up the plane, t cos 30. And that's equal to what's going on down the plane? Well, the component of the weight. 0.4 g sine 60. Of course, neither of these work out very nicely. Sine 60 and cos 30 are both root 3 over 2. More of that later. If I simply move everything to the right, then the friction is 0.4 g sine 60 minus t, which I know is 0.3 g cos 30. If I pop all that in the calculator, I get an answer of 0.84870, well, 0.849 newtons to 3 significant figures, but again I've kept the exact value. And if I want to know mu, mu is Fr divided by R, as we've seen earlier. In this case we know both of those now, so mu is 0.849 divided by 0.49. And that gives an answer which is somewhat surprising. First point to notice is it's 1.73 to 3 significant figures. Well, that's because if I'd used exact form back here, actually the answer is the square root of 3. Second reason it's possibly surprising is you might think that's rather a large value of mu, because most of the time we see mu between 0 and 1. So I had a quick look on the internet, and in fact the coefficient of friction for rubber on steel is 1.6. So this coefficient of friction is greater than that. I'm not quite sure what that tells us about the particle P in the plane, but certainly it's a pretty big coefficient of friction. Okay, we've dealt with that part of the question, and now let's consider what happens if the masses are changed so that we now have a heavier mass on the right hand side. So what's going to happen is there's an extra piece added, so the mass of Q is now 0.5 kilograms. The tension, of course, is going to change. The fact that the other particle is resting on a surface is virtually immaterial now, because once we release this system, it's going to move, particle P is going to move upwards. So let's get the weights in and consider just the vertical forces now. Well, this will be a different tension to what it was before. And we have 0.4 g down there, and now 0.5 g newtons for the weight of Q. Connected particles share the same tension, and they share the same acceleration. Q will accelerate downwards because it's the heavier particle, and P will accelerate upwards. So let's write an equation of motion separately for each particle. First of all for P. Well, for P, taking of course the direction of the acceleration as positive, I have t upwards minus 0.4 g downwards equals the mass, which is 0.4, times the acceleration. And of course I'm applying F equals ma separately to each particle. Well, there's equation 1, and let's do the same for particle Q. And now when I look at A, of course the 0.5 g force is in the correct direction if A defines the positive direction. So I've got 0.5 g minus t, which is in the opposite direction now, the negative direction, and that equals 0.5 times A, and that's equation 2. As always with this kind of question, add the two equations because it will eliminate tension. And reading from the bottom upwards, 0.5 g minus t plus t minus 0.4 g equals, and adding the right hand side, 0.9 a. Well, if I do the subtraction on the left, it's 0.1 g, which is equal to 0.9 a. So a is equal to 0.1 g divided by 0.9. Well, if I multiply through by 10, that's going to be g over 9. So therefore a equals 1/9 of g, and if you want a decimal version for that, it's 1.08 recurring, so 1.088, that would be 1.09 meters per second squared to 3 significant figures. That's the acceleration. Let's pop that back into equation 1 to find the tension. And I've chosen 1 because I can easily rearrange equation 1 by adding 0.4 g to both sides. So equation 1 gives us t equals 0.4 a plus 0.4 g. Well, I know what that is. That's 0.4 times, and for complete accuracy I use g over 9, of course 9.8 over 9. Don't forget, physicists don't use 9.81 in mechanics. And calculating all of that gives me 4.355, etc. And so that rounds to 4.36 newtons to 3 significant figures. And that concludes this Pulley question and this recording. I hope it's been useful to you.